Quite a few of my subscribers are interested in automotive diagnostics. So the question today is, do you know what truth tables are and how to use them for diagnostics? If we go to YouTube and punch in truth tables automotive diagnostics into the search, what we are going to get is a video by Humble Mechanic about automotive diagnostics. Very good and fun, informative video, but it's not about truth tables. And the other videos are about truth tables, but not about diagnostics. So we'll try to bridge the gap between the two concepts. So what is a truth table? In diagnostics, we deal with outcomes. For example, the voltage on a wire can be high or low, the state of the device can be on or off, or the switch status can be closed or open. In mathematical logic, that would be expressed as true or false outcome, and this is the main goal of truth tables, is to connect the status of several components to the status of another component. In reality, we also may need to consider more than two outcomes. For example, if we look at the voltage, we could have not only high or low states, but also the wire can be not connected at all. So we would need also consider NC, not connected outcome. Also, the state of a device can be not just on or off, but can be unknown. So sometimes we need to consider generalizations of truth tables for our diagnostic purposes. Let's look at a simple example and see how we can use the truth tables there. Let's consider a ground switch relay. So we have a battery supplying power to the PCM, and the PCM in turn is attempting to control a relay that can power some load, expressed here as a resistor. Let's first try to construct a truth table for this scenario. So the PCM control can be high, and if it's high, then there will be no current going through the relay. So the switch will be off and there will be no power provided to the load. So that allows us to fill in one of the rows of the truth table. For the PCM control being high, we are going to have relay switch open, meaning that the load will be off. If on the other hand the PCM control is low, then there will be current flowing through the relay and the switch will get closed, supplying the voltage to the load. So we will write down that the relay switch is closed and the load is on. So we constructed a truth table for the scenario where PCM control can be high or low. We could also consider another outcome where the PCM chip is not controlling anything at all, or the wire got disconnected. So we will denote that as Z. And what will happen in this case? The current will not be able to flow through the relay control, and so the switch will be off. And so we will have open for the relay switch and load will be off, just like in the case when the PCM control is high. Let's proceed further to a more interesting example where we not just construct a truth table for it, but also try to diagnose an issue. This example I would call an engine shutdown circuitry. This is because this circuit can be used to shut down an engine when something goes wrong, which is important if the engine is operating in a remote location unattended. So imagine there are a few switches that detect that something got wrong. For example, that the fuel level got low, the oil pressure got low, or the temperature got high. And if any of those situations happen, then the relay here should disconnect the ignition wire from the engine, thus shutting it down. let's first construct a truth table for this example. We will need to enumerate all possible combinations of the 3 switches, and so the total number of combinations will be 2 cubed, so 8 in total. And for each row we need to figure out what happens to the voltage on the ignition wire. For example, if all the switches are off, then there will be no current flowing through the relay at all, and so the voltage at the ignition wire is going to be 12 volts. So we will write that down as on in the corresponding row of the table. However, if the, let's say, switch S1 turns on, the fuel light comes on, and there will be current flowing through the control side of the relay, the diode, and switch S1, thus pulling in the switch and disconnecting the ignition wire from the engine. So the second row in the truth table will give us an off status for the ignition. We will have to go line by line through all the truth table and fill in the ignition wire status. When we are done, we will quickly realize that this circuit is working correctly, because the only time the ignition wire has a status on is when all the lights are off. Now, if we are into mathematical logic, we can also express it as a Boolean expression. We need to OR of all switch statuses and then negate that expression. However, if something goes wrong with the circuit, we are not going to get this truth table, and we are not going to get this expression for the ignition wire voltage. So in that case, we will need to diagnose. For example, if we arrive to the engine and the customer complaint is that, well, if the lights are off, the engine is working normally, but if the fuel level get low, the lamp lights up, but the engine continues to work. So in the second row of the truth table, instead of ignition wire having an off status, it will still be on. That's an obvious issue. Also, let's say we can figure out that if oil pressure goes down, then the engine does shut off as intended. So we can also see that in the third and fourth rows of the table, the values are correct. How we start diagnosis based on this information? Technically, if it was a computer doing this diagnosis, it would need to come up with all possible faults that can occur in this circuit. For example, diodes can be bad, the wires can be shorted to another wire or to ground or to the power, the relay can be bad, all possible faults, and focus on the faults that result in the truth table that is observed. However, a human brain is quite capable of focusing on what's important. So if we are to diagnose this system, we will immediately focus on the second row of this truth table and say, okay, the ignition wire should be off, but it's on. How can this happen? And how this can happen? It will happen if, for example, there is no current flow through the relay, this diode, and switch S1, or if the relay is bad. Also, we can note that when the oil light lights up, the ignition gets cut off, so that would mean that there is power going to the relay and there is current going through the relay when the switch S2 is closed. So the relay seems to be good. this leaves only a few scenarios. There is a problem with the wiring from this side of the relay to the diode, or there is a problem with the diode itself, or there is a problem with the wiring from the diode to switch S1. So what happened is that we constructed this truth table from the wiring diagram. We observed what actually happens, so we reconstructed partially the observed truth table, and based on the differences we focused on what's important that immediately gave us direction for our diagnosis. Now, with this information, we can go with our test lights and see if these wires are good, check the integrity of the diode, and complete our diagnosis. Now, let's proceed to a real-world example. This is based on a video from New Level Auto channel, in which Keith is diagnosing a blower motor switch and a C control on a Transit Connect van. Keith is doing it live, and it's really fascinating how he can do the diagnosis and talk about it at the same time. However, when he's doing it live, it's sometimes hard to follow the train of his thought. And so what we are going to try to do right now is to go step by step through the same diagnosis using truth tables. Of course, given a wiring diagram, the first thing that we need to do is to construct a wiring diagram. In this case, however, we have a switch that can have 5 positions, not on or off situation how we looked at before. So our truth table will have 5 rows for each switch position, and we will need to if we are interested in this voltage at the blower on terminal here on the wiring diagram. So if switch is in position 1 and it's not connected to anywhere, then the voltage coming from the motor is going to go through the resistor array, then comes here and all the way to the terminal of interest, and so we will have high voltage in this terminal. So this is what we are going to mark in the truth table. If the switch is in position 2, then it will ground this leg, and so we will get low signal at the terminal. So let's write that down in the truth table in row number 2. However, things get interesting for the switch position number 3, as this grounds pin number 2 of the resistor array, and this means that here the voltage will be 0, and thus the voltage will also be low in all this leg going all the way to the terminal again. So for row number 3 we also will have low signal at the terminal. The same thing happens for positions 4 and 5, only it takes longer to ground the terminal. We will still have low signal for those positions. Now, this is not what Keith observed in the video. Something went wrong, and for positions from 3 to 5, instead of low, it was high. So something happened to the circuit, and we need to find out what exactly. There could be several possible faults. Some wire can be shorted to another wire, possibly ground or power, or some wire can get disconnected or develop high resistance. Related question: if that terminal that we are interested in is completely disconnected, So let's see on the wiring diagram again. If we disconnect this wire completely, what will computer see? And my answer to this is that when this input is disconnected, the computer should assume that the blower motor is off and should see a high voltage at that terminal, and internally that probably will be implemented using a pull-up resistor. With that in mind, let's continue with our diagnosis. We need to imagine a fault that will result in the following truth table, where for switch positions 3 to 5 we will see high signal. And here is one possibility. If we look at this orange area and imagine that these wires and components got disconnected, what is going to happen? If switch position is 1, then the terminal is completely disconnected, and as we've discussed before, it should register the high signal. So that is consistent with what we observe. When switch is in the position number 2, it will ground the terminal and we will get signal low. However, when the position is 3, then 0 voltage appears in this junction, but there is no way for it to go back to our terminal, so it cannot go there, and we will see high signal on the terminal. The same thing will happen for switch positions 4 and 5. So this looks like a very plausible potential fault. Something get disconnected here. What we'll now need to do is to go and check this resistor and this wiring, and maybe that will turn out to be exactly our issue, and that would complete the diagnosis. So in this situation, the truth table again provides a direction for further diagnosis. So we have considered the concept of truth tables and how to use them in the diagnostics to organize the process. If this information has helped you, please comment and share this video with your colleagues. And on the other hand, if you found that this concept is too cumbersome to use in the field, please let me know as well.